Calculus, Unit 3, Day 24 notes. Our objective, understand the relationship between differentiability and continuity. So our goal is to establish a relationship between a function being continuous at a value of x and a function being differentiable at the same value. So if a function is continuous at a particular value of x, does that imply that it is also differentiable? Meaning, can we take the derivative? Or if a function is differentiable, does that mean that it must be continuous? So let's look at three functions. So what we're going to do, consider the function f of x equals the square root of x squared minus 4, x equals 2. Answer the questions that follow. So they want us to sketch a graph from your graphing calculator, so put that in, and I'll sketch it in a second. Based on the graph, if f of x is continuous at x equals 2, explain your reasoning. So let's first sketch it and then ask it. If it's continuous, then we're going to try to find the value of f prime of 2 to determine if f of x is differentiable, at x equals 2. Okay, so here's our graph. We want to find out if it's continuous. So remember, there's a two-part definition to continuity. So f of 2 has to be defined, and f of 2 equals 0. And then the limits have to be equal. The limit has to exist. So I checked the limit from the left. No. And again, why is this little space here? Well, any of those values, because -2 makes this go to 0, and +2 makes it go to 0, so everything else in between there is undefined, because you can't take the square root of a negative value. So the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. Um, and therefore the limit doesn't exist. Therefore f of x is not continuous. So let's now check to find the value of the derivative. Let's just rewrite it with a rational exponent. Now let's use the chain rule. So we get f prime of x equals 1/2 times the inside to the -1/2 times the derivative of what's inside. Hey, this 2 and this 2 cancel out. So the derivative equals x times x squared minus 4 to the -1/2. Everything being raised to the -1/2 power can be put on the other side of the fraction bar. So that'll be x squared minus 4 to the 1/2, and I'm just going to write it right as square root. So there's our derivative, and now they want to say, is it differentiable? So let's at x equal 2, so let's substitute that value in. We get 2 all over the square root of 2 squared minus 4. Hey, 2 squared is going to be 4. So the square root of 4 minus 4, square root of 0. So it's going to be 2 over 0, which, hey, that's undefined. So therefore, we find out that f of x is not differentiable at x equals 2 because f prime of 2 is undefined. So let me write that down. And again, in this example, it's not continuous at x equals 2, and it's not differentiable at x equals 2. All right, let's go on to the next example. Okay, so new function, f of x equals x to the 1/3 power plus 2, and we're looking at it at x equals 0. So let's use the graphing calculator, sketch this, and now they ask us if it's continuous. So let's look at the two-part definition of continuity. So actually it's three-part, but we stopped on the first one after step 2, so all three have to be equal. So f of 0 is defined, and it's equal to 2. Step 2 is the limit from the left equals limit from the right, and they both equal real number 2, so therefore the limit exists. So what 3 is looking for is f of 0 equals 2, and the limit of f of x as x approaches 0 also equals 2. Therefore let me write that. Therefore f of x is continuous at x equals 0. Okay, so has to be defined, the limit has to exist, and then those values have to be equal to each other to be continuous. Okay, next let's find out if it's differentiable at x equals 0. So we're going to use the product rule. So there's my original function. The product rule is 1/3 times x to the -2/3. Let's everything that has a negative exponent can be written as positive on the other side of the fraction bar. Now let's find out when x equals 0 what we get. And I'm going to get 0 to the 2/3. which is going to be 0, and then 3 times 0 is 0, and anything divided by 0 is undefined. Okay, so I find out it's continuous at x equals 0, but it's not differentiable at x equals 0. Let's write that down. Okay, so f of x is not differentiable at x equals 0 because f prime of x is undefined. All right, let's look at this last function. Okay, so we use our calculator. This is what we get. It's pretty close. Again, just ask for a sketch. Now they're asking, hey, is it continuous? So step 1, at 0, is it defined? Yes, it equals 2. Step 2, does the limit exist? Hey, the limit from the left equals 2, the limit from the right equals 2, therefore the limit exists. So last thing to check is the value at that instant, value of the function at that instant, equal to the limit at that point, and we just said they're both equal to 2. So therefore, I can conclude that it is continuous. Okay, so as we said, f of x is continuous at x equals 0. Now, last thing, they want to know if it's differentiable. So what we have to do is, let's take the derivative, and then we'll substitute in the value when x equals 0. And I'm going to end up using the power rule here. So bring down 2/3, then it's times x to the negative 1/3. Bring down x to the negative 1/3, make the exponent positive. Now let's find the derivative when x equals 0. Every place I see an x, I'm going to substitute in 0. And once again, I get 2 over 0, and that's undefined. All right, so again, f of x is not differentiable at x equals 0 because f prime of x is undefined. All right, let's answer a couple questions about this, and we'll look back at some of the pictures, so bear with me as I flip back and forth. So it says, based on what we've seen, does continuity imply differentiability, or does differentiability imply continuity? So let's think about that for a second, and let's talk about it. Okay, so what we find out here is continuity does not imply, sorry about that, continuity does not imply differentiability because at a point of inflection or a cusp, the graph is continuous but not differentiable. So let's go back to our second example. This is known as a point of inflection. Right here, it is concave up, and it's that all the way there, but then at this point right here, it then turns to concave down, and we said that it's continuous, but it's not differentiable at x equals 0. And then this next example is what's known as a cusp, where it kind of comes down to a point. It's almost like a corner. Back when we were doing um, absolute value functions, you had this corner. Well, this is known as a cusp. Again, it's concave down in this case, concave down. And at that point, it's continuous there, but it's not differentiable. Okay? And now looking at our pattern, in order for a function to be differentiable at an x value, the function must be continuous. Okay? So if it's differentiable, then it's also continuous there. All right, so let's answer this next part. In order for a function to be differentiable at a value of x, then two things must be true. These two conditions are, the first one, f of x must be continuous at x equals a. If it's not continuous, it's not going to be differentiable. And now what we have here is, and we'll look at these examples. Now let's go first, the first one. If it's not continuous, here it wasn't continuous, so we said, hey, then it's not differentiable. So if it's not continuous at that value, and in this case, this is where we're looking at x equals 2, then it's not differentiable. Okay, now let's go back here, and this is the limit of the derivative as x approaches a from the left must be equal to the limit of the derivative as x approaches a from the right. Now, obviously, what we're looking for here, and let's look at both this one. So here, as I get closer and closer, the slope of the tangent line, 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 hey, it's getting increasingly more positive, positive, positive to where it's a vertical tangent. And then here, this slope is negative, negative, further away from 0, further away from 0, further away from 0, till I get to that same vertical tangent. So that's undefined. Same thing here. Let me use this color. So tangent is negative, 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 and it's keep getting steeper and steeper and steeper until it gets to uh, an undefined slope, so vertical tangent, and same thing here, positive, 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 to the point where it keeps going until it gets to be that vertical tangent. So that's undefined. So even though it's talking about the limits being equal, it still have to be a real number. That's why I put the little star there. Okay, that'll be it for part one, and we're gonna take a look at these on part two.